When we want to compute the rate of change of a function at a point in a particular direction, we take the dot product of a vector that we call the gradient vector and a direction unit vector in that direction. This creates a weighted sum of the slope in the x direction and the slope in the y direction, and it gives us the rate of change of the function in an arbitrary direction. For the gradient vector, we write grad f, or in the text, they'll write out the word grad f, so that you'll always know when you see it that we're thinking about the gradient vector. The gradient vector is the object that gives us information about the derivative in multivariable calculus, because by giving us information about the rate of change of the function with every variable in this vector format, we're able to compute the rate of change of the function in an arbitrary direction. We're now going to try to think about some properties of the gradient vector by doing some reasoning about derivatives. So what if we think about the directional derivative at a point where the direction is given by a vector along a contour? Well, in that case, instantaneously, we stay on the contour as we move in that direction, and so the value of the function can't possibly be changing. We expect to get a directional derivative of 0. Since we can compute the directional derivative via a dot product of the direction along the contour and our gradient, and we know that we're getting 0, we know from the properties of the dot product that the angle between these needs to be 90 degrees. We know that these two vectors are perpendicular to each other. So here I've just drawn in the grad f direction, and instantaneously it needs to be perpendicular to the contour lines. We can use the geometric definition of the dot product to think a little bit more about the directional derivative and the gradient. So using this geometric definition, we see that the directional derivative comes from the magnitude of the gradient vector times the magnitude of our direction vector times the cosine of the angle between them. But our direction vector is a unit vector, so this simplifies immediately to the magnitude of the gradient vector times the cosine of the angle between them. Looking at this geometrically, if here's our gradient vector and here's our direction vector, this length times the cosine of this angle gives us the component along this direction. This is generally true of the dot product. If we take the dot product of any vector with a unit vector, then we find the length of the vector times the cosine of the angle, which is giving us the component of the vector in the direction of the unit vector. Thinking specifically about the directional derivative, if we want to maximize it, we would maximize it by maximizing cosine theta. That means we maximize the directional derivative in the specific case where the direction in which we're computing it is completely aligned with the direction of the gradient vector. So that means the directional derivative is maximized when the direction is parallel to the gradient. How do we find that direction? Well, to create a unit direction vector, we can take the gradient vector and just divide by its magnitude. This will produce a unit vector in the direction of the gradient, and so this is the unit vector that will produce a maximum directional derivative. What will that maximum rate of change be? In that maximal direction, the directional derivative is just going to be given by the magnitude of the gradient, and that's because the magnitude of this vector is 1, and the cosine of the angle between them also yields a 1. And so the largest slope that we can find for the function at a point is the magnitude of this gradient vector. To recap, the directional derivative of f in the direction of u at the point AB is this gradient vector of f at AB dotted with the direction vector, and the gradient vector is perpendicular to a contour line at the point AB. The directional derivative is maximized when we move in the direction of the gradient of f at the point AB, and it has the maximum value of the magnitude of this gradient vector evaluated at that point.